Right until now, if you wanted to get the coordinates of the zero of a function, all you needed to do was to equal that function to 0 and solve it for x. So for example, if you would have 2x squared plus 3x minus 1, and you wanted to know the coordinates of the zeros of this function, just equal it to 0, solve it for x, and you have the coordinates of the function is going to be the outcome of this equation, and that will be it. But there are situations in which you don't know how to solve the equation. So there are some equations that cannot be solved using an algebraic method. But you may still want to get the value of the zeros up to a certain precision. In these cases, it's going to be possible to find solution up until any arbitrary precision that you need in the first place. This, what we're going to learn in this topic, is completely different from what you have learned up until now. Up until now, you are learning tools in order to get algebraic methods that allow you to solve equations. This is completely different, as you're going to see. This is going to be attempt error and figuring out ways to narrow down your search up to a precision that is going to be tinier and tinier and tinier until what you predefined as being satisfactory in terms of precision. You're going to learn two different methods. The interval estimation, which is also called the change of sign methods, and the fixed point iteration. But you should only use these if algebraic methods are not available, all right? Because algebraic methods allow you to get the values of the zeros to an infinite number of decimal places, that is, to an infinite precision. And these, no, these you have to predefine on the question itself. Predefines the precision that you are going to find the zeros, and you have to continue working until you get to that precision, but that's the top that you get. It's not going to be infinite, all right? So only use them if algebraic methods are not available. And in each case, you have to transform the equation into a function and sketch it to make an informed judgment on what method to use if the question itself doesn't tell you which one to use. And always state the precision of the answer. But anyway, the question is going to ask you to go to up to a certain precision, but you should state it at the end anyway, all right? So let's look at the interval estimation. For any function that has a zero, what happens a little bit before and a little bit after that zero? What's going to happen is that a little bit before, either the function is going to be negative or positive, and a little bit after it's going to be positive or negative, all right? So basically, what is going to happen to the function? The value is going to change from a negative to a positive, or from a positive to a negative. I'm not contemplating here, you probably already noticed, situations in which the zero is also the inflection point. Either imagine this being as the vertex of a parabola, of an inverted parabola, or something like this, all right? So in these situations, f of a times f of b is going to be negative, right? Makes sense. Now that the position of the root is narrowed down to the interval ab, what can you do? You can break this down into smaller pieces, all right? And narrow down your search for the interval in smaller intervals, right? So now that the position of the root is narrowed down to the interval ab, in which a and b are two consecutive integers, it's time to dig in and find it with more precision. The first method is the decimal search. So what happens? You break this down into increments of size 0.1. So you're going to try to look for a, then a plus 0.1, then a plus 0.2, a plus 0.3, until you notice another change of sign, all right? When this happens, the root is now trapped between two consecutive decimal numbers, all right? For the sake of argument, let's say that this is 1 and 2, right? Then you are going to start narrowing down the search to 1.1, 1.2, 1.3, 1.4. So let's say that now the sign changes between 1.3 and 1.4. So you know now that the root is in between 1.3 and 1.4. It's already a much tinier interval. See what's happening here? So what is the next step? Now do intervals of 0.01 so that the interval becomes narrower and narrower and narrower. All right? Take now increments of 0.01 and continue doing the same method. All right? So here is an example that I just made up. The interval between the interval begins being between 1 and 2. Then do the first decimal search, and you'll figure out that the root is in between 0.6 and 0.7. Narrow it down to the hundredths, and now it's going to be 0.63 and 0.64. And what do you know if this happens? You know that the root is either, you can put it like this, 0.635 plus or minus 0.005. This is the maximum error. Or that the root is 0.6 precise to one decimal place. This is the one I prefer, all right? What you know over here, you can be sure about the second decimal place, but precise to one decimal place, you are absolutely sure that the root is 0.6. You know what I mean? You can continue this search as far as you want or as far as the question asks you to go, all right? The other method is called interval bisection. And instead of you breaking down the interval in equal parts, you just break it in half and do the search between the two extremities. Let's see what it says. Bisect the interval AB and test for half of it, f of half of it. And this will show in which half of AB the root is. So let's say that this is A and this is B, right? F of A is positive, f of B is negative. So you know that the root is somewhere over here. Then test half of it, okay? So again, positive, negative. If this is what? If this is positive, means what? Means that the root is now over here. If this is negative, means what? Means that the root is over here, all right? This one speeds up the process, something that the first one that you learn doesn't, all right? So bisect now the new interval again and do the same thing over and over again, okay? This is easier to do, actually, with questions than explained, all right? Both methods will automatically produce the error bounds. Again, situations that you have to pay attention to is when the maxima or minima is on the x-axis. I mentioned this a little while ago. And when you have several roots close together, okay? This is very uncommon for you to happen. And if you continue bringing the search to narrower positions, you would notice that this would happen, okay? For example, if you would stop over here, you would assume that you only have one root when in fact you have three. This is very uncommon, okay? Another situation that you have to pay attention to is the discontinuity of functions. You don't have that many, all right? If you would test between this interval, you would say that this one is positive and this one, for this value over here, was negative, and assume that there was a root over there, when in fact what you have is an asymptote, all right? But again, this is very rare for you to find in situations in exams, okay? So the best way, again, for you to understand how this works is to practice with exercises. So I invite you to solve a few in the next videos.